Okay, so we have a question about 9.2, number 9. Okay, here we are. It says consider the equation as follows. Use the completing the square process to write this equation in the form x plus d squared equals e, and enter your results below. Okay, so let me write this down on the paper, and then we'll go to the paper. All right. So x squared plus 10x equals negative 16, and they want us to write it in the form x plus d squared equals e. Okay. And then they want us to solve the equation. Okay. So let's come back to the paper and we'll take a look. All right. So there we are. X squared plus 10x equals negative 16. We want to write it like this. All right. So we want a perfect square on the left-hand side. And so when we talked about completing the square, we said that you can add something to this to make it a perfect square. And that thing we always add is always exactly 1/2 of this number squared. So 1/2 of 10 is 5, and 5 squared is 25. So what I'm going to do is add 25 to both sides of this equation. Completing the square process, you always take 1/2 of this number squared. Now, it's important that that only works once you've factored out the number that's in front of the x. Now, in this case, the number in front of the x, in front of the x squared. In this case, the number in front of the x squared is 1, so that's already done for us, all right? If this was not a 1, we'd want to divide through by that first, okay? Or factor it out, either way. You just want to get it out of there, right? But once you've done that, we just take 1/2 of this number, square it, and add it, and we get this. And now this is supposed to be a perfect square. And sure enough, it definitely is. It is x plus 5 squared. And so I think we've done it. We've written this thing like this. I can see that d is 5 and e is 9. And so that's the completing the square process. Okay. One thing we might want to look at is what if that coefficient was not a 1? What if this was 2x squared plus 10x equaled 16. We'll see what happens. Okay. So what would I do? I would start by dividing through by 2. All right. So divide everything by 2. And now I have the coefficient of 1 over here, so I can do the same thing. So what would I do? I would add 1/2 of this number squared to both sides. Okay. Now, what is that? Well, 1/2 of 5 is 5/2. You square it, you get 25/4. Right. And now this is a perfect square. This is actually x plus 5/2 squared. If you square that out, you get this. And I can simplify the right-hand side, right? 25/4 plus -8. -8 is the same thing as -32/4, right? -32/4 plus 25/4 is -7/4. Right? So that's what we would do there. It just occurred to me we didn't actually finish this problem up here. We didn't solve it. All right, so let's go back up and solve it. Let me try to leave both things on the screen while I do that. All right. So if you wanted to solve it, what we would do is we would just take if something squared equals a number, then you know that thing that was being squared is equal to plus or minus the square root of that number, right? Which is plus or minus 3 in this case. So subtract 5 from both sides, you see that x is equal to -5 plus or minus 3. And we're actually getting two solutions here. -5 minus 3 is -8. -5 plus 3 is -2. So there's our two answers for x. Okay, so I hope that clarifies things. Any other questions? Another one, good. Section 8.8, number 15. All right. So 8.8, number 15. Complex number system. Here it says, perform the indicated operation and simplify. Express the answer in terms of I, the complex number that represents the square root of -1. Okay. All right, so let me write this down and then we'll go to the paper. All right, here we have it. There's a negative in here. I almost forgot to squeeze it in. Remember that whenever you have the negative under the square root, it comes out as an I. So I can rewrite this right away as 3 plus square root of 49 I, right? And 9 plus the square root of 64 I. Negatives come out as an I. Okay, so I can simplify this some more because I know what the square root of 49 is. Right? Square root of 49 is 7. And the square root of 64 is 8. So we've simplified it a little bit in terms of I. But what we haven't done yet is multiplied it out. Okay, so yeah, perform the indicated operation means do this multiplication that's in here. So we have to multiply. Okay, so when I multiply, I do 3 times 9, that's 27. 3 times 8i, 24i. 3 times 8 is 24. 7i times 9, well, 7 times 9 is 63. And there's an I there, so it's 63i. 7 times 8, 7i times 8i. Well, 7 times 8 is 56. And I times I is I squared. Now remember, I is the square root of -1. So I squared is -1. So this is actually, I squared here becomes a -1. And that's one of the tricks here. So this, we can combine like terms. 27 plus, this is a -56. 56 times -1. So 27 plus -56. Well, that is, yeah, we got to subtract these. So I'm thinking it's a 29, -29, right? 27 minus 56 is -29. And then what about these other terms? Well, we have 24i and 63i. So these are like terms, so we can combine these. So that gives me 87i. And I think that's the form that they wanted in the final answer. Yeah, it's an answer in terms of I, so that's what they would want. Okay, any other questions? Nope, not seeing anything. Okay. So, just want to remind everybody, an exam is coming up. I think it's 2 weeks from today. Let me just double check the schedule here. And remember, the schedule is posted in the course materials on My Open Math. Is it 2 weeks from today, or it's 1 week from today? It's next week. So the exam is, am I looking at the right schedule? Yeah, April 30th is our exam. So that exam is going to cover chapters 8 and 9. All right, so everything that we've talked about in both those chapters. We're going to finish up chapter 9 today, and we're going to have Tuesday to review. So I'm not going to cover any new material on Tuesday. It's all going to be review stuff. So I'd like you to come to class next Tuesday with questions so that we can look those over. Tomorrow I'm going to try to put together some problems that you can focus on for the types of questions that I would be asking for you to show your work on. All right, so I'll ask you to upload your work, and I want to remind you that that work is going to be worth a substantial amount of the exam grade. So make sure you can do that part correctly. Okay. So I'll email you about the types of questions that I might ask you to show your work on. I'll try to put that together over the weekend. Maybe tomorrow, we'll see. Okay. And remember, come to class next Tuesday with questions. Let me see if, have I opened up the homeworks for you yet? Okay, so what I'm gonna do is I'm gonna make copies of the homework assignments. I don't think I've done that yet, so that you can practice them over the weekend to kind of help you review for the test. So older assignments that have already been, expired, you can still go in and work on problems of that kind. All right, so I'll do that tomorrow as well. All right, so for today, though, we are going to, I want to review one more word problem. We were doing applications problems. So I want to do one more of those, and then we're going to cover the next section, which is, what was the next section? It's graphing quadratic functions using their properties. So we're going to start thinking about what the graphs of second-degree polynomials look like. Okay? All right, so let me take the screen down to the document view, and we're going to look at this word problem. Okay. It says, Marianne, and by the way, this is section, let me just give you the section number here so you can refer to it in the book. This is section 9.5 we're dealing with here. Applications. We're applying what we've learned to solve some real life-like problems here. So it says, Marianne just returned from a visit with her grandchildren back east. The trip was 2,400 miles from her home, and her total time in the airplane for the round trip was 10 hours. If the plane was flying at a rate of 500 miles per hour, what was the speed of the jet stream? So the jet stream is an air current that is kind of high up in the atmosphere. We're not too high. It's where the same elevation that planes travel. And it's kind of like a steady stream of air, and airplanes can tend to take advantage of this. And sometimes if you fly in a plane, the pilot will mention that because we're in the jet stream, we might shave, half an hour off our trip or something like that. So even though the plane is exerting, 500 miles per hour with their engines, the jet stream can kind of push you a little bit faster. Although if you're going against the jet stream, it can slow you down. So this is what we're dealing with here. So I think what we want to do is keep in mind, by the way, you might need to read these problems like 3 or 4 or 5 times before you kind of get the sense of it. So don't feel bad if that's the case. That's totally normal. We want to try to, once we've got a kind of handle on it, we want to try to draw a picture of what's going on. If we can do that, that usually is helpful. So the trip is 2,400 miles. And it's, we're doing a round trip here. Okay, so we're going from point A to point B, and that's 2,400 miles. All right, and there's a jet stream that's blowing one of the two directions. I don't know which way it's blowing, but there's this jet stream that's blowing at some speed, right? But we don't know the speed of that jet stream. Okay, let's say R equals the speed of the jet stream. They want us to find it. Usually if there's something they want you to find, that's what you want your variable to be. Almost always, that's what you should do. What was the speed of the jet stream? Let R be the speed of the jet stream. Why am I using the letter R? Well, R stands for rate. So the rate at which we move is the speed. Now the plane here is traveling at 500 miles per hour, right? So when we travel with the jet stream, we're going to be traveling at 500 miles per hour plus R, right? So the speed with the jet stream is R plus 500. And when we're going against the jet stream, so the speed against the jet stream, we're going to take 500 miles per hour and subtract R. Okay. And then what else do we know here? We know the total time for the trip was 10 hours. Okay, so we've got distances, we've got speeds, and we've got times. How are all these things related? Well, you might recall that the distance traveled is equal to rate times time, right? If you're going 60 miles per hour and you travel for 1 hour, you go 60 miles. Or if you went 60 miles an hour for 2 hours, you traveled 60 times 2, 120 miles, right? So you multiply rate times time to get distance. So that might come in handy. That's a relationship we might be able to use. So let's see here. The rate, so the total time for the whole trip was 10 hours. We don't know how much time she spent traveling in any one segment of the journey. So I can't say that it was 5 hours this way and 5 hours back, because actually if she's going faster in one direction, it'll actually be less than 10 hours. All we know is the total time. Let's see. Actually, what I do know is that the sum of those two times is 10 hours, though. So we can think about the time in one direction and then the time back. And we know that the sum of those two times is 10. So there's an equation we can look at. Time 1 plus, time 2 we know is 10. So there's an equation. So let's work with that. See if we can turn this into an equation that we can work with here. Time in one direction plus time in the other direction totaled to 10 hours, right? Okay. Well, I can express time in terms of distance and rate because I can solve this for time, right? So this equation, if we divide both sides by rate, the rates cancel on the right-hand side, and I see that time is the same as distance divided by rate, all right? So time 1 is the distance divided by the rate in that direction. Now the rate in that direction is, say that's the speed, that's the maybe where we're going with the jet stream in that direction. That's R plus 500, right? The time in the other direction, say it's when we're going against the jet stream, that's the same distance, right? But it's, it's 500 minus r, because that's, again, distance divided by rate equals 10. Moreover, we know a little bit more. We know the distance, right? The distance is 2,400, and that's the same in both directions. So there's our equation. It's 2,400. Let me put these in the same, kind of write in the same way. Instead of writing r plus 500, I'm going to write 500 plus r plus 2,400, 500 minus r equals 10. Okay? So let's do this. Let's work out this equation now on another sheet. Okay. So that's what we have to solve, because we're looking for the rate. So if we just solve this for r, we'll have our answer. All right, well, I've got some fractions here. Whenever we have fractions, what do we want to do? We want to clear those denominators out. So I want to multiply by something that will cancel this and also cancel this. So why don't we just do the product of these two things? That's the least common denominator, or the least common multiple of the two denominators. Right? So I'm going to multiply both sides times the product of these two things. So we're going to do 500 plus r times 500 minus r. I'm going to multiply that times this stuff. And I'm going to multiply it by the other side too. Okay. Now, when I multiply, I distribute, right? So I'm going to have 500 plus r times 500 minus r times this guy. Then I'm going to have plus 500 plus r times 500 minus r times this guy. And then I've got equals. So that's just, now this guy, I think we can simplify this. This is a plus b times a minus b. That's a difference of squares, a squared minus b squared. Right? A plus b times a minus b is a squared minus b squared. So this is just 500 squared. So that's 25, oh, forgot the 10 there. Don't forget we have a 10 out front. 10 times 25,000 minus r squared. Right? That's what this can be written as. Now let's see what we can do with this stuff. Well, it's not so bad because these things cancel. These things cancel. All right. So let's see here. 2,400 times 500. Well, let's see. What's 24 times 5? It's 120. And then I've got 0, 0, 0, 0. So 120 with 4 zeros after it. When I multiply this times the 500. Right, so 120 with 1, 2, 3, 4 zeros after it. Minus, this also hits the r, so I got minus 2,400 r. And then this thing, 2,400 times 500, same thing. 120 plus 1, 2, 3, 4 zeros, plus 2,400 r, right? Multiply by the r. And then on the right-hand side, we have 10 times this stuff. So that's going to add a 0 here. Oops, 25, 0, 0, 0, 0, 0, minus 10r squared. Whew. All right. Well, not too bad because some things are going to work out nicely here. I got minus 2,400r plus 2,400r. So those kill each other. I've got 12 with 5 zeros, another 12 with 5 zeros. That makes 24 with 5 zeros. Okay, see, it's getting simpler already. Oh, well, look at this. If I add 10r to both sides, 10r squared rather, and then subtract 24 with 5 zeros after it from both sides, what happens? Well, the 10r squared ends up over here, and these things cancel off over here, and I get 25 with 5 zeros minus 24 with 5 zeros. That's just 1 with 5 zeros. Okay. Divide both sides by 10. Right? So this is an equation we can solve pretty simply. If something squared equals this, that means r must be equal to plus or minus the square root of that. The square root of this, you just cut the number of zeros in half. Excuse me. So that's just plus or minus 100. Okay. It's plus or minus because we didn't indicate whether we were going against the jet stream or with the jet stream. Right? So it could be with us or against us, plus or minus. They just want the speed of the jet stream, so 100. Okay. Speed of the jet stream, the speed of the jet stream was 100 miles per hour. Okay, so that's a problem. That's an application problem. Application to solving problems involving squares. Okay. So any questions on that? Okay, not seeing anything yet. I'll keep my eyes open though if anything pops up. So that's it. That's the application section, right? And there's only one more section we need to cover in Chapter 9, and that is Section 9.6. That's graphing. We're going to graph polynomials of second order. Okay. So that is the next thing we need to look at, right? So graphing. And the last thing in Chapter 9. And there's really not much left of the course. So, okay. What I want to do is, well, let's see. Let's go down to the paper. I'll write down the general idea of what we're doing, and then I'll show you some demos on the graphing calculator on the computer. Okay, so Section 9.6, we are graphing what they call quadratic functions. Okay. So a quadratic function is a function that it's a polynomial that whose highest degree is 2, and actually is degree 2. So the degree is exactly 2. So a function, remember, we had this function notation. Here's a script letter f. F of x, this is a function that's going to take a number x and produce a new number. If it's a quadratic function, then it looks like this. Okay, where a, b, and c are numbers. So for example, let's do a number of examples. You could do f of x equals, let's do 7x squared minus 14x plus 8, something like this. This is a quadratic function. A is equal to 7. B is equal to negative 14. and c is equal to 8. Okay. Another example of a quadratic function, this one I might call g instead of f. I don't need to use the letter f here. I can use any letter I want. You might just have something like x squared plus 3. That's a quadratic function. For this one, a is the number in front of x. That's a 1. B, I don't see a bx, but that means, that's okay. That just means b is 0. Right? And c is equal to 3. So that's a quadratic function. Another function I might call h of x. All right, so the function h of x is, let's say it's, let's do, well, okay, can I make this into a number? Yeah, I'll make it a 6. Let's do negative 6 x squared plus 2x, something like this. Right? That's a quadratic function where a is negative 6 and b is 2. And you don't see the c here, but that's okay. That's what happens when c is 0. Sometimes you'll see things mixed around a little bit. So I might have a function k where you might have 5 minus x squared plus 3x. That's not in the same order up here, but it's still okay. It's still a quadratic function. The a is negative 1. The b is the number for the x, that's 3. And the c is 5. Different order, but still the same thing. You could rewrite it so that this is like this. In fact, you could rewrite it like this. Right? Same thing. And now it matches up term by term. So these are examples of quadratic functions. Now what we want to do is we want to talk about how to graph these. What do they look like when we draw, sketch the graph? Okay, so what I want to do is let's go to a graphing calculator and just take a peek.
Professor.
Yeah.
For the second one.
Yeah.
The 3 is C?
Let's go back. Hold on. Yeah, let me write down. For the first one, A is 7, B is negative 14, C is 8. For this one, A is 1, B is 0, C is 3. For this one, A is negative 6, B is 2, and C is 0. And for the last one, A was negative 1, B was 3, and C was 5. Any other questions? I have a question. Why didn't I start recording? Oh, I did. Okay, good. I don't remember hitting the button. I've taught 3 classes now, and so everything's blurring together. Okay, good. I'm glad I did. I was worried. Okay, any other questions? Okay, let's go to the graphing calculator then. All right. There's a nice one online called Desmos. And I've showed it to you before in class. So you just type desmos.com and you can come to this nifty graphing calculator. So here I've inserted a quadratic function, right? And what it's going to do is draw the graph over here. And what I want to do is just explore a little bit. What do the numbers A, B, and C have to do with the graph? All right, so I've got sliders here for these values. So whatever number you see here next to the letter A, B, or C is the number that you should imagine being up there in the expression for the function. So let's mess with A first. What happens when I wiggle A around? All right, I'll give you a second to guess. What would happen if I change A? Just think about what might happen here. I'm going to change the number in front of the x squared. I'm going to leave the B and the C the same. Okay, let's see. I'm going to make A bigger. And there we go. Our graph is getting more and more narrow, right? Why is that happening? Well, x squared is kind of the dominant term here. That's that when, for large values of x, this is going to overpower the other 2 terms. So when you make A big, it's going to make everything big. And so this graph is growing very fast. Now, if I make A smaller, it'll flatten out, right? And in fact, when you make A negative, look what happens. The whole thing turns upside down. And then the same kind of thing happens when you make A a big negative number. So when A is negative, the graph opens downwards. And when A is positive, the graph opens upwards. So that's the important feature that I wanted to point out involving A. Now notice when A is 0, what happens? Well, when A is 0, there it is, I get a line. And that makes sense because if A is 0, the x squared term is gone. I just have a function that's bx plus c, which you could write as mx plus b, right? And we know that's the equation of a line. So that makes sense. We're going to be considering the case when A is not 0, so you can ignore that situation. But I just wanted to point that out. All right, so when A is positive, it opens up. When A is negative, it opens down. I'm going to skip B for a second. Let's look at what happens with C. What would C do? If I change C, what's going to happen to the graph of this function? Just think about it for a second. See if you can determine what's going to happen. Okay, I'm going to leave A and B the same, and I'm going to wiggle C. So let's increase C. Graph goes up. Decrease C, graph goes down. This should make sense because all I'm doing is taking the stuff that depends on x over here, and I'm just adding a number to it, right? The number adjusts the height, right? When I graph something, I'm graphing the height for every x. And here I'm just adding a value to every single thing I've computed. So everything just gets shifted up, C units. So if I make C big, stuff gets high. If I make C small, it goes lower, and negative, it goes below the x-axis there. So C is very simple. It just moves the graph up and down. All right. B is the weird one. You can imagine what B might do. And this is, you know, when I saw this, I was thinking, oh, wow, that's neat. Not what I expected. B, look what it does. It keeps the graph exactly the same shape, but the intercept there, the y-intercept is staying the same. That's kind of interesting, right? So it's just shifting the graph around, but keeping the y-intercept exactly the same. That's kind of cool, but very hard to describe. All right, and because of that, we're actually going to try to find another way to represent these functions, so that with something that's a little bit more easy to interpret than B here. We're going to write it down in a different form, so that we have a parameter that's not as confusing as B, because I find this a little bit non-intuitive what's going on here. All right, so let's go back to the paper here and just make note of some of the things we saw. All right. So one observation, some observations. When A was greater than 0, that means the graph opens, oops, I'm having a hard time writing today, opens upwards. When A is less than 0, the graph opens downwards. And by the way, what is the name we give to that graph? That's a special kind of curve. It's called a parabola. As long as A is not 0. We saw when A was 0, it becomes a line. All right? So as long as A is not 0, this is a parabola. So instead of writing the word graph, I could just write the word parabola there, or vice versa, right? So we made that observation. We also made the observation that C affects how high the, this letter C here at the end affects how high the graph is, right? And it actually had to do with its y-intercept, right? So C, well, let me write it this way. The y-intercept is a point. 0, comma C is the y-intercept. Okay, and that should make sense, because if you want to find the y-intercept, what do? you plug in 0 for x, because the y-axis is exactly where x is equal to 0, right? That's where the y-axis is drawn, right, on 0 on the x-axis. So if you want to find the y-intercept, you set x equal to 0, and you see what value you get. So if you just take the function, f of x equals ax squared plus bx plus c, and you plug in 0 in place of x, look what happens. You get a times 0 squared plus b times 0 plus c. Well, all this stuff is 0, so you just get c. And that is an algebraic way of determining that. We saw it graphically, but this is an algebraic way to see it, right? So 0 comma c is the y-intercept. B was a little more mysterious, so I'm not going to write down anything about b here. Okay. So there are some other aspects of that graph that we want to explore. We saw that it was a parabola, right? It's got that bowl-shaped, it's a bowl-shaped curve. One nice thing about parabolas is that they're symmetrical about a middle line called the axis of symmetry. Okay, so let's just talk a little bit about parabolas. A parabola can either open up or down, but it is symmetric about some vertical line. This vertical line is called the axis of symmetry. The parabola can open up, or like I said, it can open downwards. It can be skinny or it can be wide. But there's that line that goes right through the middle of it. And it's the same, it's a mirror image across that line. And that's why they call it symmetry. It's symmetric across that line. There's another important feature of a parabola, and that is this point right here. The point that's either at the very top of the parabola or at the very bottom of the parabola. It's either the minimum or the maximum point. That's called the vertex. That's the vertex there. That's the vertex over here. So we want to be able to identify the vertex of our parabola and also try to find its axis of symmetry. Okay. There's some other things that we might want to know about our parabola. We talked about the y-intercept, right? So I could try to squeeze it into that picture, but I think things might get a little messed up, a little crowded anyway. We can also talk about the intercepts, right? So we know that we have a y-intercept, and we might have x-intercepts, although we don't have to, right? Because I think you saw that we could lift this parabola up by adjusting that parameter c. And if you lift the parabola up high enough, it won't even intersect the x-axis. Or if it's opening downwards and you push it down low enough, it won't intersect the x-axis. So it doesn't have to have x-intercepts, but it might. And it can have at most, how many? Let's see, by the shape of this curve, I can't get any more than 2 x-intercepts. So you can have at most 2, you can have as few as 0. And you can even have 1, exactly 1. I'll let you think about how that might happen. These are the x-intercepts. So we've already talked about how to find the y-intercept. So the y-intercept, all we do is we just look at f of 0. Just plug 0 into our function. You get a number. The y-intercept is the number 0 comma c. Whatever number you got when you plugged in 0. Okay. Sometimes people say that the y-intercept is the number 0 comma f of 0, because that's how you get c. You plug 0 into the function. So these are the same. That's an equal sign. How do you get the x-intercepts? Well, we've talked about this in the past, how we get x-intercepts of functions. What we're looking for is where the function is, where the f of x is actually has height 0. So for the x-intercepts, we're actually going to set f of x equal to 0. So instead of putting the 0 in the parentheses over here, we're going to put it on the other side of the equal sign. And then we're going to solve for x. And the x-intercepts will be the points x comma 0, where the x comes from whatever we solved there. So it's a little bit more involved to find the x-intercepts. Okay, so let's take a function. I'm going to go look at one of the ones from your homework here in the book here. Find the intercepts. Okay, so here's a problem they have here. It says f of x equals x squared plus 7x plus 6. And they want us to find the intercepts. Okay. Okay, well, y-intercept, super easy. All I do is compute f of 0. So for the y-intercept, very simple. Just compute f of 0. F of 0 is 0 squared plus 7 times 0 plus 6. I just replaced x with 0. I get 6. Right, so my y-intercept is the point 0, comma 6. There's my y-intercept. Be sure to write it as a point. Don't just write 6. It is a point, so give its x and y coordinates. And its x coordinate will always be 0. I mean, that's how we found it. We set x to be 0. Right? But the y is what you've got to find here. What about the x-intercepts? The x-intercepts, we're going to set the function equal to 0, putting the 0 on the right-hand side. Well, what's the function? It's this. So when I say this, what I mean is x squared plus 7x plus 6 is equal to 0. So we've got to solve that. And this is something that you'll have to use the techniques that we've been talking about all through chapter 9. Right? There's several ways to solve an equation like this. Right? The first thing we learned was factoring. So if you can factor it, I think that's the best way to go. If factoring doesn't work, you can use the method of completing the square. That was a method that we used to solve something like this. And if that doesn't work, you can try the quadratic formula. That will always give you the answers. But I think in this particular case, I think factoring is the way to go. It's very easy to factor this one. This one factors as x plus 6 times x plus 1. And so I can see the solutions. The two solutions are x equals -6 and x equals -1. So I have two intercepts in this case. I have the intercept -6, comma 0, and I have the intercept -1, comma 0. So these are my two x-intercepts. Notice that the x-intercept will always have a 0 in the y as its y coordinate, because the x-axis goes through, this is the x-axis here, it goes through y equals 0 here. So this will always be 0. Okay? And furthermore, we can tell just by looking at this whether it opens up or down, right? We just look at that A here, the number that was out front. Is it positive? Yes, so it opens up. So they only wanted us to find the intercepts, but while we're here, why don't we just say this parabola opens up. And I can tell that since the leading coefficient, the A, is greater than 0. And so with that information, we can actually get a kind of a rough idea of how to graph this, all right? So this is one way to graph a parabola. Find its intercepts, find which way it opens, and then, you know, draw the graph from that. So if I had some axes here, I could, let's see, I've got my intercepts at negative, let's say this is -6, this is +6. Say this was 6, that was -6. And then, okay, that means halfway there is 3. Right. I got some axes here. The y-intercept was 0, 6, so that's right here. Right. The x-intercept is -6, 0, and -1, 0. Right, so like this. How can I get a parabola out of here? Remember, it's just a parabolic shape. It can't wiggle more than once. It's got to have only one curve in it. So it must look like this. It must go just, I missed when I drew, but it must look something like this. So that's finding the intercepts is one way to graph it. However, as we pointed out, we observed that if C is very large and it opens upwards, or if C is a large negative number and opens downwards, you may not have any x-intercepts. There may be none, in which case you've only got 1 point. You may only have the y-intercept. So how can you draw the graph if you don't have any x-intercepts? So this method is not that great. It works sometimes. If it has x-intercepts, this is fantastic. If it doesn't have x-intercepts, it's not going to work so well. Let's see if I can think of see if we can make a function that doesn't have x-intercepts. So let's take a look at f of x equals, let's do x squared minus 2x plus 10. I think this one will give us some trouble, okay? I just made this C really big, right? So I think it's big enough that we're probably not going to intercept the x-axis. So y-intercept I can get, right? Y-intercept, no problem. You're always going to have a y-intercept. Just plug in 0 for x, and you just get a number here, so we know the y-intercept is 0, 10. All right, great. What about the x-intercepts? Those are the ones that require more work. So I'm going to set this thing equal to 0. And then I'm going to solve it. All right, well, I can't factor this one. This one's not easy to factor. I could try completing the square. Let's just dive in and use the quadratic formula on this one. Or you know what? I think completing the square is good practice. Let's complete the square. All right. So when we complete the square, what we try to do is get this part by itself. Well, how did we do that? Yeah. So let's subtract 10 from both sides. And then I want to add something to this to make this a perfect square. Well, what do I always add? I add half of this term squared. So half of -2 is 1. 1 squared is 1. So I'm going to add 1 to both sides. So I get x squared minus 2x plus 1 equals -9. Just to note what we're doing, make it very clear. We're completing the square. So actually, this step is completing the square when we add the 1. That's making this a perfect square. So this is x minus 1 squared on the left. Okay. If you factor this, you get x minus 1 squared. And now look what happens. I've got something squared is a negative number. Right? Now I could stop there and say, well, wait a minute, I already know something's wrong. Or I could say, oh, I could keep going with this and say, well, then x minus 1 is equal to plus or minus the square root of -9. Right? That's plus or minus square root of 9i. That's plus or minus 3i. Right? So x is equal to 1 plus or minus 3i. These are complex numbers. These aren't real numbers. So they don't exist on the real number line. They don't exist on the x-axis. So if I were to graph this one, I know I have my y-intercept up here at 10, but the x-intercepts, there aren't any. It's somehow, the graph goes up. I don't know if it goes like this or like this. I really don't have enough information to tell what side it's on and what it's doing. These complex numbers aren't on the x-axis, so I know it doesn't cross the x-axis. So it's something like this, but my graph is kind of hard to ascertain with the information that we have. So what we're going to want to do is explore some of that other information that we talked about, all right? Some of that other information that we talked about were these things: the vertex and the axis of symmetry. If we could locate the vertex or the axis of symmetry, we would be able to tell where this parabola is, all right? So that's what we want to do. We want to learn how to find these things, because that will allow us to draw the graph even if it doesn't have x-intercepts. So x-intercepts are useful, but not always, okay? So let's talk about how to find that stuff, and it all comes from the standard form of a parabola, okay? So the standard form of a parabola is as follows. Oops, that's an x minus, is it? Yeah, H comes before K in the alphabet, so it probably comes first here. Okay. A times x minus h squared plus k. Right, this is the standard form. If you can get your parabola to look like this, then we can say a little bit more about it, okay? Instead of the other form that we had, which was this. That's a way to write it, but if we can get it to look like this, we can say a little bit more. Okay, I think we're back. Okay. All right, so that's what we want to do. We're aiming for this. So how do we get something like this to look like something like that? All right. And then I'll show you why we can get the vertex and the axis of symmetry from this, okay? So how do we get this? That's our goal. It all comes from completing the square, and that's why completing the square is such an important thing, okay? So let me give you a function. All right, let's take the function 7x squared minus 14x. Okay, that is a quadratic function. It is of this form, where a is 7, b is negative 14, and c is 0. Okay, so it's definitely one of these. Now I want to try to put it into that other form that I wrote down. All right. Now what was characteristic of that other form? Well, it has something x minus something squared, right? So I want to try to get that, and I get something like that by completing the square. So that's what I want to do here. I want to complete the square. So I think about how to do that. It's always adding. To complete the square, you add 1/2 of this squared, right? So what I'm going to do is I'm going to add, oops, that's a minus. I'm going to add 1/2 of 14 squared. Well, 1/2 of 14 is 7. 7 squared is 49. Now, I can't just write this, though, because I have just changed this, right? I've added 49 to it. It is now different, right? I want to keep the same function. I don't want to change to a new function. I want to be dealing with the same function. So if I add 49, I've made a new function. I've changed its value. So if I want to keep it the same, I have to also subtract 49. So now what I've done is I've added 0, because 49 minus 49 is 0. So I haven't changed it at all. right? This is the same as this. If I simplify this, I get back to this. But what I've done is I've made a part that is a perfect square, right? Oh, wait, I forgot about that. Oh man, I messed up one part though. Sorry, rewind. If I could edit this video, I would just edit that out. I forgot, when we complete the square, we have to factor this out first, all right? So let's rewind a little bit. I have to first factor out the 7, all right? So factor out the 7, x squared minus 2x, okay. Okay, so let's start over here. So I want to make this a perfect square, all right? So the stuff inside those brackets, same idea. I'm going to add 1/2 of this squared, okay? So I'm going to take 1/2 of 2, it's 1, and square it, it's 1. All right, so that would be, if I did this is the same thing I was saying before. This, I've changed it, I've added 1 to it. So to make sure I have the same thing, that I haven't changed anything, I have to also subtract 1. So I've added 1, subtract 1, I haven't changed it at all. But what I've done, picking up where I was at before, what I've done is I've created a piece that is a perfect square, right? So that is a perfect square. I can write that as something squared minus 1. What is that? Well, it's always x, and then you just take half of this, right? So it's x minus 1 squared. Okay. So by adding and subtracting the same number, I didn't change it, but I made part of it a perfect square. Okay. Now I can distribute the 7 through. So I get 7 times x minus 1 squared minus 7. Okay, we have just put it into this form, right? The a here is the 7, the h is the 1, and the k is the negative 7. See, it's plus k, but I'm subtracting 7, so k is negative 7. So this is in the standard form of a parabola. So that shows you that you can do this. If there was a number tacked on the outside, if I had like a 3 out here, well, that doesn't matter. You just kind of do the same thing and just keep that 3 on the outside, 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 and then just simplify it one more step. Negative 7 plus 3 is negative 4. So not a big deal. If there was another number over here, works the same way. All right, you just kind of carry that along and then just simplify it at the end. Okay, but what can I do with this? Well, when you look at this guy, you can still find the x-intercepts and the y-intercepts exactly the same way we did before, just by solving those equations. But you can also see something else. When you can think about, when is this thing the smallest, right? Well, it's when this term is the smallest. This is the only thing that depends on x, all right? This is the smallest when it's equal to 0, because I'm squaring it. That's the smallest this number squared can get. Can't be negative. You can't square a number and get negative. We're not talking about complex numbers here. So it's the smallest when x makes this stuff 0, and that's when x is 1. All right? So that is the vertex of my parabola. Remember, we said the vertex happens when it's the smallest. Now, if it's opening downwards, it's when it's the biggest. But it's the same thing. It's the thing that makes the stuff in the square 0. All right? So I can see that the x-coordinate of my vertex is 1. Now, when x is 1, this whole thing is 0. Right? And the y, then I just get, if I plug in 1 for x, I get negative 4 for y. So my vertex has coordinates 1, negative 4 here. Okay, so the vertex is the point 1, negative 4. This is the thing that makes the square part 0, and this is the number that's on the outside. Okay, and moreover, the axis of symmetry is the line that goes through the vertex. So that's just the line x equals the same thing, negative, in this case, 1. So the axis of symmetry is x equals 1. So if I wanted to graph this, I know that I can just very easily find the vertex (1, -4). My axis of symmetry is right here, x equals 1. And does my parabola open up or down? Well, I could go back up here and see that this 7 on the outside is the same as this 7 on the outside here. It's positive, so I know it opens up, right? So I know my parabola is going to go upwards like this. And even if it didn't have x-intercepts, I can still get a kind of pinpoint where the graph is, okay? So let me go back to this description here. Maybe I'll, okay, well, I guess I can't fit both of these on here, but this I can say a little bit more. The vertex is going to be the point h comma k. And the axis of symmetry, axis of symmetry is the line x equals h. So once I write it in this form, I can just read off what the vertex and axis of symmetry are. The only thing you have to be careful about is that h is being subtracted, all right? So it's whatever number you're subtracting, all right? So if I have a, running out of, give me 1 second. Oh, I found a sheet. Okay, thought I was out of paper. All right. So let's just look at some other parabolas in standard form and just read off their axis of symmetries and vertices. Okay, so let's look at -9 x minus 3 squared plus 8. We'll look at x plus 2 squared minus 3. We'll look at 4x plus 7 squared, all right? And what I'm going to do here is we're going to identify, for each of these, we're going to identify the vertex, and we're going to identify the axis of symmetry. Okay. Okay, so for the first one, remember the vertex, let me get both of these on the same screen. Okay, good. The vertex is just h comma k. Right? So I can see that I'm subtracting 3, so that's my h, and I'm adding 8, so that's my k. So the vertex here is just it's just 3. That's where you have to be careful. It's the number I'm subtracting, so don't put a -3 in here. I almost made that mistake, right? It's whatever you're subtracting, that's the number. So I'm subtracting a +3. I'm not subtracting -3, that would be x plus 3. I'm subtracting a +3, so make sure you put a positive here. My axis of symmetry is just x equals that number. Okay, let's go to the next one. We have to be careful here. I'm looking at x minus h. Which number am I subtracting to get x plus 2? What do you subtract from x to get x plus 2? You subtract a -2. So my x coordinate of my vertex is a -2. You subtract -2, it results in +2. So notice that this sign is the opposite of that sign there. And my y coordinate of the vertex is always this number out here. Now in this case, it's the plus k. What am I adding to subtract 3? I'm adding a -3. My axis of symmetry is just x equals whatever this number is. X equals -2. Okay. And this one down here, I see my a is 4 here. I got x plus 7. So what am I subtracting to get plus 7? Well, I must be subtracting a -7 to result in plus 7. So the x-coordinate of the vertex is -7. I don't see a number out here. So what am I adding to have nothing happen? Well, 0. Add 0, nothing happens. So the vertex is -7, 0. The axis of symmetry, x equals -7. So we have a vertical line indicated for each one, the axis of symmetry, and we have the vertex of these parabolas. So once we get it into standard form, we can read these off, and these are very useful in helping us graph. Okay? Let me see if I have, I want to go through one more problem where we complete the square to put it in standard form, because I know that people have a kind of a hard time with that, all right? So let me go through another example of putting a parabola into standard form, okay? So let's go down here. Write in standard form. Okay. Let's see, let's do 5x squared plus 30x plus 12 is my function, okay? So I don't know, maybe it's p of x this time instead of f of x. Doesn't matter what the letter is. Okay, so what we're gonna do is we're gonna put it in that standard form. We can identify the vertex and the axis of symmetry. Well, what did we do before? We ignored this number on the end, just leave it to the end, all right? And what we did is we factored out the guy in front of the 5, in front of the x squared, because that's how we complete the square. We have to make sure this is a coefficient 1 first. So I'm going to factor out a 5. Just leave that 12 outside. Don't worry about that. Just focus on this stuff, all right? All righty. So now what's inside these square brackets is what I want to complete the square for. So inside these square brackets, I'm going to have to add and subtract something to this so that it's a perfect square. Really, perfect square, I mean, to complete the square, we just add something, but if we want to keep it the same, we need to also subtract something here. So it's always 1/2 of this squared. So 1/2 of 6 is 3. 3 squared is 9. So I'm going to add and subtract 9. So in essence, I've done nothing. I've added and subtracted the same number, so nothing happened, which is good because I want to keep it the same function. But what I'm getting here is that this thing here is a perfect square. So that is going to be some square. What square is it? Well, it's always x plus half of this. So there, I've got my square. Now I distribute through the 5. Okay. Five times -9 is -45. And there's that 12 hanging out on the outside. I finally get to deal with the 12 at the very end. At the very end, I combine these, and I've got my final answer. -45 plus 12. I make these hard for myself. Minus 33, right? Oh, my camera's dying. Okay. I think it'll last. All right. This is the last problem we're doing. So. Okay. So now that I've got it in standard form, I can identify the vertex and the axis of symmetry, right? The vertex and the axis of symmetry. The vertex, well, it's the number that makes this 0, right? That's the x coordinate, so that's -3. And then the y coordinate out here, -33. The axis of symmetry is just x equals -3. And so if I were to graph this, I know it opens upwards because that number on the outside here is positive. So I know I'm drawing a parabola that opens upwards. Got this axis of symmetry at x equals -3. The vertex is way down here at -33. So it looks something like this. And you could find these intercepts as well, right, by doing what we did before. So you can also get the intercepts. If you want to find the y-intercept, just plug in 0 into this equation, this expression, or this expression. Either one, they're the same. If you want to find the x-intercept, set these things equal to 0 and solve. And by the way, this will be much easier to use to find the x-intercepts because we've already completed the square. So finding the x-intercepts will be very straightforward. It'll be quite easy to get those. Okay, so that's the usefulness of getting it in standard form. This form is much more useful for dealing with parabolas than that first form I showed you. So this is what we'll try to be doing in this section, and then drawing the graph. So any questions? In My Open Math, on the homework there, I'm going to have some problems where you will be sketching the graph of these parabolas. So you'll have to do all this stuff and do the graphing. And then remember next week we'll be reviewing. The test will be on Thursday, so we'll be reviewing on Tuesday. So please look through. I'm going to post copies of the homework so you can go, review those. Please look through those things and come with questions on Tuesday. Okay. So any other questions?
Are you sending this video full? Because
yeah,
I was.
I'm recording this whole thing. I'll post it just like I've posted all the other ones. How long is the exam going to be? I'll design it to be done in an hour, but it might take some of you 2 hours. I guess I'll probably post it like the last one and give you 4 hours to do it, just to be safe, just so that in case there are any mishaps with internet connectivity or something like that.
Okay, would you send more videos for this chapter, or are you taking class?
I think that I wasn't planning on making any more videos for this. I was going to upload this video and then you could use this as a reference. You might find some other videos within the homework set. Some of the homework problems come with videos attached.
Okay. You're sending the homework today, right? On this chapter?
Yeah.
Okay.
Any other questions? Okay, so I'm gonna